Thanks a lot, Lieven, for the introduction, and thank you all for coming. Yeah, so my second tutorial, as Lieven said, will be about tensors in statistics and data analysis. Just to recap what I went through in tutorial number 1, although I won't be assuming that you weren't already using very much from my previous tutorial. But there I talked about this process of going from linear algebra to multilinear algebra and some of the challenges that arise and how these challenges relate to algebraic properties of tensors. And I was focusing on various aspects of the singular value decomposition. So singular vectors, notions of rank, low rank approximation, and analogs of these different concepts for symmetric tensors as well. So in this tutorial, I'll be taking a more application-driven perspective. So for the previous tutorial, the motivation was really that we have these concepts from linear algebra and we want to try to extend them to multilinear algebra. Here, the viewpoint is a little bit different in that I'm thinking about applications, and I'm going to present some different applications where tensors arise. And then we'll look at the best way it makes sense to use tensors to understand these applications. All right, so the first setting that I'll talk about is looking at probabilities and statistical models. So settings where it makes sense to consider tensors of probabilities, where each entry is a certain probability. I'll then discuss some situations where we can encode data in a tensor. And we hope that this encoding is a useful way to keep track of some data. So for instance, one example of this that may be familiar is taking a probability distribution and encoding it by its moments. But there's also other encodings. So I'll talk about the signature, which takes a path like these pictures here, and again, encodes it as a sequence of tensors. And then another situation where tensors arise in looking at data is where the actual entries of the tensor are some data values. Each entry is a data value. So here's an example of a particular data set. So this picture represents a order 5 tensor. So we have different cell lines, different ligands, different doses, different time points, different output measurements. So those are our 5 indices. And once we fix the value for each of these, we get a number which we obtain from some experiment. And yeah, the focus will be on the tensor decompositions that naturally arise from studying these applications. So we may have to let go of the tensor decompositions that we want to arise based on our appreciation of linear algebra, and instead look at those that actually do end up being natural to study in these contexts. And I'll focus on the algebraic properties of the tensor decompositions as we go along. And I should say as a disclaimer that for the purposes of this talk, I'll use the word tensor almost interchangeably with a multi-indexed array of numbers, with the invitation to you all to think about what may be the natural transformation rules to work with in various settings. All right, and yeah, please stop me at any point if there are any questions. All right, so I'll start with some probability tensors. So the starting point for this is we have some random variable, let's call it y, and it takes values in a finite set, which I can call the numbers 1 up to n. Then the probability mass function of this random variable is a vector of numbers, where the ith entry of this vector is the probability that the random variable takes the value I. So for example, I could think about a die with like a 6-sided die, then I would have a random variable in 6 states, and its probability mass function would be the probability that it lands on each of its 6 sides. All right, and then this can be extended to looking at multiple random variables simultaneously. So if I take now random variables yj, which each take values on some finite set, 1 up to nj, let's say, where j goes from 1 to d, then their joint probability mass function we can encode as a tensor of size n1 by by nd, where the entry of the tensor at the index I1 up to ID is the joint probability that Y1 is in state I1 and YD is in state ID. Okay, so here's a picture of the tensor here, and each mini cube of the tensor is a particular probability. Okay, so then in particular, we're dealing with a tensor of non-negative entries that sum up to 1. All right, so why is it useful to think of our probabilities as being entries of a tensor? Well, one possible justification is that the random variables have this structure that is this joint probability mass function across different random variables. So we want to keep them separate. So then it makes sense to use a tensor to sort of keep this multi-index structure. But that's not full justification. The hope is that we can study properties of this tensor and connect the properties of the tensor to the properties of our probability distribution. And then considering this not just for one tensor, but for a collection, we hope that there are some nice families of tensors that we can understand, and that these will have some statistical meaning. So these will correspond to some statistical models that could be of interest. All right, so that's the idea. And the first example of this is to look at rank 1 structure. So we have our random variables, yj, and we have their probability mass function, which we saw on the previous slide, gives this tensor. Then if our random variables are independent, this means that the entry of the tensor at index I1 ... id is, well, it's this joint probability. But if they're independent, then this joint probability factors as the product of the probability that y1 equals I1 times ... times the probability that yd equals id. So for instance, if we're thinking about our random variables as being some dice or weighted dice, then we might expect that they will all be independent. And so we would roll a collection of dice and record the tuple of numbers that we get in our tensor. Okay, and this means that the tensor x can be factored as an outer product of vectors, where each vector is the probability mass function of just a single one of our random variables. All right, and this factoring structure of a tensor is familiar to us. It's a rank 1 decomposition of the tensor. But it's also a non-negative rank 1 decomposition, because we want to interpret each of these vectors as themselves being vectors of probabilities. So this is the vector x1, whose entries give the probability mass function of random variable y1. But the reason I've written non-negative in brackets is that if we start with a non-negative tensor and it's rank 1, then we can choose the vectors in its decomposition to also be rank 1. So this non-negativity we get for free from our rank 1 decomposition. All right, so then the picture to have in mind is we have our space of all tensors of probabilities. So these are tensors of non-negative entries that sum up to 1. So that's this tetrahedron in these two examples in this picture. Well, actually, it's the same example from two different viewpoints. And then we have a particular subset of tensors in this space, which have some special structure. And this is given in this example by this surface. So this is the surface of rank 1 tensors, or equivalently, the statistical model corresponding to independence between our random variables. Okay, so in the previous slide, I was saying we hope that families of tensors that are quite natural correspond to statistical models that make good statistical sense. And here we see the first sort of promising example of this, which is that rank 1 tensors correspond to the independence model. Okay, but as in other contexts for the study of tensors, rank 1 is very special and often a bit too special. And similarly in statistics, this full independence between all of our random variables is very special and often can't be assumed to hold in practice. So we want to go beyond this correspondence between rank 1 and independence to something a bit more. All right, so this was our first example of rank 1 and independence. How can we go beyond this to have a larger statistical model, or equivalently a larger set of tensors? Well, one possibility is to look at conditional independence. So this notation here means that y1 is independent of y2 given y3. Okay, so once we've fixed a value for some third random variable y3, then y1 and y2 are independent. But if we don't fix a value for y3, they need not be independent. Okay, so what does this condition tell us about our tensor of probabilities? Well, okay, we have xi1, i2, i3 is this joint probability that y1 is in state i1 and so on. This conditional independence statement tells us that the entries of this tensor can be written as this factored form. So as a i1 i3 times b i2 i3. And we can see that if we fix the value of i3, then this gives us something rank 1, just the outer product of two vectors. And this is telling us that the slices of our tensor are rank 1. So once we fix the value for i3, we get something that's rank 1. All right, and statistically, this is sometimes written in this notation. So here we have random variable y1, and here we have y2, and y3 sits between them. So this notation captures that once we fix y3, then y1 and y2 are independent. Okay, so this can be extended to more general graphs as well. So we can consider this graph here where we have 5 random variables. And now we want to consider the probability tensors that represent random variables that factor according to this graph. And how this works is we go through the cliques of the graph.
Anna, let me interrupt you. There is a question. Let me see if I can unmute Edina. Okay.
I was just asking whether the graph is directed or undirected.
Okay, yeah, that's a great question, and both settings are studied. Here, I'll be focusing on the undirected case, but there's analogs that hold for directed graphs as well.
Okay,
Yeah,
thank you.
thanks for the question. All right, so in this conditional independence example, we have this graph and it corresponds to a particular factorization of our probability tensor. And this extends to more general graphs. So the factorization of our probability tensor that this graph represents, we go through the cliques of the graph. So this graph has 4 cliques or maximally complete subgraphs. So there's the clique on vertices 1, 2, and 3, and then on 3 and 4, 4 and 5, 2 and 5. So the statistical model represented by this graph is the set of all probability tensors that factor as this product of an order 3 tensor and 3 order 2 tensors. So that's this this factorization here. All right, but this is not just a set of tensors. It has some algebraic structure. So we can understand the collection of all tensors that that factor in this form, for example, or that factor according to the structure of some other graph. And we can see that this
Anna,
conditional...
let me interrupt you. There is a question from Joseph.
Yep.
Yeah, hi. So this structure, you don't want just that it factors, but that it factors in certain groups, right? So, but if I understand, or you'll accept any factorization in terms of 3, 2, and 2, or do you have this? Do you care that it's 3, the first 3 factors?
Okay, yeah, that's a good question. Yeah, we care that it's the first 3. So this labeling of the vertices corresponds to which indices we want to be together in this decomposition, as that expresses the order 5 tensor as the product of order 3, order 2, order 2, order 2.
Okay.
Does that answer your question?
Yes, thanks.
Thank you.
Yeah. I mean, okay, in principle, it's possible to consider a union of such things where you don't really care about which indices go together. But for the statistical setting, yeah, this is important. And these, I should say, are undirected graphical models on finite random variables. All right, so we can consider the set of all tensors, order 5 tensors in some dimensional space that factor in this form. So this is not just a set, but has nice algebraic structure. And we can see from looking at the decomposition that conditional independence corresponds to various rank 1 conditions on various slices of the tensor. And this leads to conditional independence ideals, which are studied in algebraic statistics. And so you obtain some equations that describe your space of probability tensors. So for example, here is an example of this. And then to describe the set of actual probability tensors that factorize, you want to restrict these equations to the polytope of non-negative tensors with entries summing to 1. So here we've got the whole space of tensors, or a cartoon of the whole space of tensors, and here we've got the restriction of this space to the set of probability tensors. And this intersection gives us an algebraic description of the statistical model. All right, but then maybe one downside of these conditional independence statements, although they're very useful and widely used, is it's still given by these rank 1 conditions. All right, so how can we go beyond rank 1? Well, the way to do this is via hidden variables. So now let's assume I have some observed random variables, x1, x2, and x3, and I have a hidden variable y. So here is the graph that encodes the dependencies between these random variables. So let's see, if this was fully observed, as in the previous examples, then this would give me an order 4 tensor that factors as a product of 3 matrices. But now I want to consider the random variable y as being hidden. So this means summing over the possible values that it can take. So I end up with an order 3 tensor whose indices are labeled by the 3 observed random variables. And it's given as a sum over the hidden variable of our 3 matrices. So I said that the hidden variable takes values in 1 up to r, and the reason for this choice of letter r is that this is giving us a rank r decomposition of our order 3 tensor x. Okay, but it's not a usual rank r decomposition because we require that the factors are also interpretable as tensors of probabilities, or in this case, matrices of probabilities. So we want all the numbers that appear in this sum to be non-negative. Okay, and that's the next correspondence between a set of tensors and a particular statistical model, that the set of tensors of non-negative rank at most r corresponds to the setting of a mixture model where we have a single hidden variable and it can take r states. All right, and we can also do this other group.
There is another question, just a second.
Okay, great.
From Joseph.
Yeah. So could you say what techniques there are for determining the non-negative rank of a tensor?
Yes, I will say something about this. The answer will be there are very few techniques. I don't know if you'll be happy to hear that or not happy to hear that, but yeah, I'll talk about that a bit later.
Thanks.
Yeah, thanks. Thanks for the question.
Okay.
All right, so we can also consider other graphs. So for instance, if we have a graph that looks like this with a layer of hidden variables and a layer of observed variables with edges given by a bipartite graph in between them, then this is called a restricted Boltzmann machine. And we can ask, okay, what is the set of tensors, non-negative tensors, that factor according to this graph here? And we can work this out by looking at the fully observed setting and then summing over the hidden variables. And in this case, we get a Hadamard product of non-negative rank R tensors if each of the hidden variables have R states. Okay, so for example, let's see, this is if you have 3 observed states. So this is an order 3 tensor and 2 hidden states. So if we just consider this this block here, then we'd get this Hadamard product of 2 order 3 tensors, each having non-negative rank at most R. All right, so we can do this in general. We can take a particular graphical model and it will translate to give us a set of tensors. Okay, and the set of tensors is, in all of these examples, a semi-algebraic set. Okay, so it's described by some equations and some inequalities. So we can ask ourselves, well, what are the equations and inequalities? How can we decide what the non-negative rank of a tensor is, for example? And that's what I'll talk about here. So in this special case where we have a single hidden variable, the question is to determine the non-negative rank of a tensor, or to see which non-negative ranks can even occur.
Anna, there is another question from Arpan Paul. Yes.
Yeah. So in your, I think a couple of slides before, when you said there are more than one hidden variables, are we assuming that the hidden variables are independent also, or there are dependencies, or it doesn't matter?
Yeah, we can consider either case. So always the recipe is to look at your graph. So for example, in this graph, and look at the cliques of the graph, and these give the subtensors that you're going to multiply together, and then you sum over all the hidden variables.
Okay.
So I mean, often in practice, it makes most intuitive sense from the statistical perspective to have hidden effects that are not themselves connected to one another. So that's that maybe underpins the popularity of using models like this, because if you have hidden variables and they themselves are connected, then it can become more difficult to interpret which of them is responsible for some observations. But yeah, in principle, you can do either. Thanks for the question.
Thank you.
Okay, there is a second question. Gero Frieseke.
Yes, thanks, Anna. So just to follow up on Paul's question, so the answer is yes in your formula, right? Because when you factor the x I1, I2, I3 this way, you are assuming the two hidden, I guess that's for two hidden nodes, you are assuming them to be independent, right?
That's right. Yeah, that's right. And that can be seen from the picture by the fact that there's not an edge between these two hidden nodes.
Okay, cool. I got it. Thanks.
Great. Thanks, Lucas.
Okay, thank you.
All right, good. So we have these statistical models. They describe semi-algebraic sets, and we're interested in knowing the equations and inequalities of these semi-algebraic sets. Or maybe we're not so interested, but for the purposes of this slide, this is what we're very interested in. And for the setting where we have a single hidden variable, we saw that this corresponds to non-negative rank, so the non-negative rank of a tensor. And we can ask the question, which non-negative ranks occur? So this is fully understood in, I believe, only the case of 2 by 2 by 2 tensors. So let's look at the case of 2 by 2 by 2 tensors. And let's assume that all the entries are not only non-negative, but actually positive, because it makes the description of the inequalities a bit easier. All right, so here's a cartoon picture of what happens. So here's our space of all 2 by 2 by 2 tensors. And it separates into different pieces. So we know that the complex rank of a 2 by 2 by 2 tensor will generically be 2. So everywhere in this rectangle here, we have complex rank 2. If we look at the real rank, which I talked about in my first tutorial, then we can have real rank being either 2 or 3. So here's our real rank 3 locus here, or a cartoon for it. And then everywhere outside of this is real rank 2. Okay, and the boundary doesn't look like an oval. The boundary between these two is given by the hyperdeterminant, which looks more like this. Okay, and then we come to our non-negative ranks. So the non-negative ranks that can occur are 2, 3, or 4. And by sampling in the probability simplex, we can compute the relative volume of these different sets of tensors, and this is what we get. All right, and now we can also give equations for the different pieces. So the non-negative rank 2 setting was studied in this paper here of Alman, Rose, Stumfuzz, and Zwiernik. So the non-negative rank 2 locus separates into 4 pieces. So one of the pieces is given by this system of binomial inequalities here. And where do the other 3 pieces come from? Well, just by relabeling, so by swapping indices 0 and 1. And the non-negative rank 3 has 3 pieces. So we studied this in joint work with Guido Montufar, and one of the 3 pieces looks like this. And again, similarly, you obtain the other pieces by swapping indices 0 and 1. Okay.
Anna, in the meantime, there is a whole questioning back and forth in the chat space. I'm giving the word to the person who asked the last question, and that is Jordan Ellenberg.
Oh, hi, Anna. Boy, my question was very naive, but I guess now I've been unmuted, so I'm going to ask. I don't even know, even in the matrix case, is non-negative rank different from rank, or is this something where the difficulties come just in the tensor context?
Yeah, that's a good question. So that also occurs in the matrix case. So the non-negative rank of a matrix can differ from its usual real rank.
Although is that story completely understood, or is even that hard?
Yeah, so it's somewhat, I think it's well understood and has a nice, I'm not going to say it's fully understood, but it has a nice geometric interpretation in terms of nested polytopes, and
cool.
yeah, it's very nice. But as you say, for matrices, we don't have this distinction between real and right. Complex rank. Yeah, thanks.
Okay, please continue.
Okay, great. So this is just a few examples where it's known how we can test or compute the non-negative rank of a tensor. In general, this is very difficult to do. And testing the non-negative rank gives us a membership test for the statistical model, the model with a single hidden variable that takes a certain number of states. All right. And since tensor networks are probably more familiar to people in the tutorials audience than graphical models, I wanted to just mention the connection to tensor networks. So I've been describing this recipe that takes us from a graph to a decomposition of a tensor. So for instance, we can consider this graph here, where I want to think of this row of variables as being observed and this row as being hidden. Okay, so now I'll construct the set of tensors represented by this picture. So we look at the cliques of the graph, which are given by this clique here, this one here, this one here, this one here. Then the tensor is the product of this order 2, order 3, order 3, and order 2 tensor. And then I sum over the hidden variables. So that I sum over the possible values of the indices J1, J2, and J3. And this may be recast as a tensor network. So in this case, we get this tensor network here, where now instead of the arrays labeling cliques of the graph, they're now labeling vertices of the graph. And the hidden variables now become these complete edges that connect to vertices, and the observed variables are these dangling edges that aren't connected to another vertex. So this tensor network may be familiar as being a building block to matrix product states. And this connection between graphical models and tensor networks is something that that I looked at together with Alina Rebeba in this paper. And various other operations in the world of graphical models also translate to the setting of tensor networks. So in both communities, it's often important to sum over indices. In the statistical setting, this means marginalizing or having some hidden variable. And in the tensor network setting, this is used, for example, in computing expectation values. All right. So what this says to people who work in tensor networks is, if once you have a fancy new algorithm, tell your statistician friends about it, because they might want to hear about it too. Okay, all right. So then beyond testing membership in statistical models, we often want to find a point on a model that is the best fit to a point that's not on the model. Much like for a tensor or a matrix, we want to find its best low rank approximation. So this is a statistical analog to this question. All right, and one way to do this is via maximum likelihood estimation. So the maximum likelihood estimate is the point, or it might be multiple points, on the model that is most likely to give our data. Okay, so here's the picture. We have the space of all probability tensors, and then we have our statistical model, which is some subset of this space, maybe with some nice algebraic structure. Or here's an even lower dimensional cartoon. So we have our probability tensors. We have our model, which is this black curve here. And then we have some data, which, okay, we can compute non-negative ranks and see if it lies exactly in the model. But in practice, most likely the model will be very small and the data will not lie exactly on the model. So we can search over the model to find the point that gives the best fit to the data. And that point will be the MLE. So in this cartoon here, we search over the model, and here's our maximum likelihood estimate. All right, so how do we compute it? Well, our data, so this blue point here, is given by a probability tensor whose entry I1 ID is the fraction of times that we observed the state I1 ID. Okay, I guess this line is a bit confusing with two equals signs. So maybe imagine big brackets around here. So this entry of our empirical probability tensor is the fraction of times that we observe this tuple of states. So for example, if we're rolling several dice, the entry at 1, 1, 1, 1, 1 will be the number of times that when we rolled all of our dice, they all came up with a 1. Okay, and then we need our measure of distance, or in this case, divergence. And this is given by the likelihood function, which is the product over all of our multi-indices of our unknown probability raised to the power of our data observation. Okay, so this is just the likelihood for a random variable on discrete finite state space. Okay, or often it's preferable to work with the log likelihood. So we can take the logarithm and get this summation instead. Okay, so our goal is to maximize the log likelihood as we vary over the model. And this can equivalently be thought of as minimizing the Kullback-Leibler divergence from our data point U to a point P on the model. And such approximations of non-negative tensors were studied in this paper of Lekeng, Lim, and Pierre Camon. Okay, so now we have a new notion of best rank 1 approximation of a tensor, given by this notion of maximum likelihood estimation. Okay, so we saw before that the independence model translates to tensor being rank 1. So if we consider the case of 2 binary random variables, then our model is parameterized by non-negative 2x2 rank 1 matrices. Okay, so what's non-negative rank 1 2x2 matrix? Well, it's a 2x2 matrix, which is rank 1. Oh, and with entries summing up to 1. Okay, so it's parameterized by this, like this, by 2 lambda parameters for the rows, which should sum up to 1, and our mu parameters for the columns that sum up to 1. Okay, so yeah, this is a rank 1 matrix. Its determinant is 0, it's non-negative, and its entry sum up to 1. Okay, good. So now we want to study maximum likelihood estimation for this model. So our data is this tensor, or in this case, it's a matrix. So at entry uij, we get the fraction of times that we observed state I for the first random variable and state j for the second one. And then we can compute our likelihood. So we have our unknown probabilities raised to the power of our data observation. And this can be rewritten just by collecting terms like this, where U0 plus means summing over the possible values for the index that I've written with a plus. All right, and we can look at when this is maximized, subject to these conditions, and we get our maximum likelihood estimate. So here are the best choices of our parameters. And this is our best rank 1 matrix. Okay, and we can observe that this is not the best rank 1 matrix that we would get by doing usual best rank 1 approximation, like with respect to Euclidean distance. Okay, maybe it would be strange if it was, since it's a different notion of distance or divergence. And it's also a dice formula because it gives our optimal point as a function of our data point. So it's it's just given by this combination of our input data rather than the solution to some system of equations and so on. But in general, the maximum likelihood estimate will be given either as the solution to some system of equations or obtained by some local optimization methods. But yeah, this algebraic kind of approach can be applied when we've got no hidden variables, or is also starting to be applied in the first cases where we do have hidden variables, where this then works through looking at the different pieces of the boundary of the model. So, for example, this was studied in this paper of Alman et al. From 2017. Okay, so I will now move away from considering probability tensors and move away from non-negative rank, and instead talk about moments and cumulants of a distribution. All right, so these are tensors that arise when looking at random variables that now don't need to take values in some finite state space, but can take values in, for example, r to the d. Okay, so I've got some random vector x, which takes values in r, d. So for example, I could consider a d-dimensional Gaussian. So x, this notation here means x is normally distributed with mean vector mu and covariance sigma. So mu is then a vector of length d, and sigma is a d by d positive definite matrix. So this gives our familiar sort of multivariate bell-shaped object. All right, and given a distribution like this one, you can compute its moment tensors, which are the expected value of the random vector tensor product with itself some number of times. So this will give us an infinite, well, in principle, infinite sequence of tensors. But in practice, we'll stop doing this. Oh, sorry. Sorry, I'm just receiving a call, but I won't pick up. Okay, can you still see my slides? Yeah, sorry about that.
Yes, it's fine.
Okay, so we get some sequence of moment tensors. So for example, our first moment is just the expected value of x. Our second moment is the expected value of x tensor x. Our third moment is the expected value of x tensor x tensor x, and so on. Okay, so for example, for our d-dimensional Gaussian, the first moment, this is the expected value of just our random variable. So this is our vector, our mean vector mu. Our second moment is given by mu tensor mu plus sigma, and we can compute the third moment, and so on. Or it's often nicer to work with cumulant tensors instead of moment tensors. And for instance, for the d-dimensional Gaussian, if we work with cumulants, this also gives us in principle, infinite sequence of tensors, which encodes our distribution. And our first cumulant is our mean vector mu. Our second cumulant is the covariance matrix sigma, and the higher order cumulants in this particular example vanish. All right, so then we have some particular tensors. For instance, you could consider this the collection of all d by d by d tensors that have a decomposition into this form. So they'd be a sum of something rank 1 plus some other stuff. All right, and why is this a nice construction to do? Well, the hope, as we saw before, is that properties of these tensors will translate to properties of our probability distribution. And this is a topic with a lot of progress recently and probably in the near future as well. So I'll just mention a few works in this sort of direction by people who will be participating in this long program on tensors. So we can look at various different tensor decompositions and use this decomposition of the tensor to estimate parameters in the statistical model. So this is described, for example, in this paper of Anand Kumar et al. called tensor decompositions for learning latent variable models. We can look at the dimension of the space of tensors, and this will tell us something about the identifiability of recovering parameters in the model from its encoding via these moments. And yeah, this is looked at in a paper of Amendler, Ranestad, and Stamfors called Algebraic Identifiability of Gaussian Mixtures. Or we can, we can look at certain equations in the entries of our tensor. And this tells us something about model membership. So as we saw in the finite case with testing non-negative rank, this can also be done in this in this setting where our random variable takes values in some other space like RD. So this was looked at in a recent paper of Rabev and Sebi, and also in other works as well. This isn't intended to be a complete list at all, just a sampling of results. All right, so I'm now going to move to talking about a different way to encode data using a sequence of tensors based on a paper of Chen, whose name is not KT Chen KT, so one of these KTs should not be there. And it's based around paths. Okay, so we've got a path, which is now a function from the unit interval 0, 1 into some vector space like RD, and it sends our parameter t, which you can think of as some time, for example, to its tuple of coordinates in this vector space. All right, so now the signature is, as we saw for moments and cumulants on the previous slide, it's a sequence of tensors. So the first tensor will be a vector of length d, then we have a matrix, a d by d matrix, then we've got a d by d by d tensor, and so on. And the entries of this, of each of these tensors are certain iterated integrals. Okay, so for example, the ith entry of the first order part of the signature is given by this formula here. Okay, and we can extend this to entries of the higher order signatures. So there'll be iterated integrals. I haven't written down a general formula, but this is the idea. So the ijk entry of this third order tensor is this triple integral involving the ith, jth, and kth entries of our path. So the ith, jth, and kth coordinates of the path. All right, and why would we do this? Well, we hope that properties of the tensors translate to properties of the path, properties that we might be interested in, and therefore that encoding our path as a tensor will be a useful way to represent it. For example, if we want to classify paths as part of some data analysis pipeline. Okay, and the signature encoding does capture some structure of the path, but it's not always so direct to see what exactly it is capturing. So for instance, here are some examples. So these four paths, this black path here, and this green one, pink one, and yellow one, are four paths which all have the same signature up to level 3. So if you truncate their signature after this third term and ignore the higher order terms that appear, then as far as the signature is concerned, these paths are the same. Okay, so then the third order signature would be useful if we're working in some context where we do want to view these paths as being more or less the same. And we can see that they have some similar properties. So since the first entry in the signature has to be the same, we want the difference between their start point and end point to all be the same. Okay, and and they all start and end at the same value. And we can also interpret what it means for the second order part of their signature to be the same in terms of various signed areas of the path. Okay, so what do signatures of paths look like?
Anna, there is a question from Joseph.
Yes, so if the path is analytic or, I don't know, some category of nice function, can you recover it from its signature?
Yes, that's a good question, and I'll come to that. I'll come to that shortly.
Oh, sorry. Keep on.
No, thank you. That's yeah. Thanks for the question. Keep them coming.
Okay.
Okay, all right. So what do signatures of paths actually look like? Well, maybe the easiest example of a path is just a linear increment from some point to another point. So the path TV, where V is some vector direction. And its signature is nice, especially if you like rank 1 tensors. So the first entry is just the vector V, the second order part is V tensor V, the third order part is V tensor V, and so on. And we can write this, okay, so we can think of V as being a vector in some vector space, then we can write the signature sort of concisely as the exponential of V. So as the power series 1 plus V plus a half V tensor V, and so on. And this lives in the tensor product of all vector spaces V raised to different powers. So in this tensor algebra T of V. All right, and now we can wonder how this extends to piecewise linear paths. So here are some examples of piecewise linear paths in R3. So we got this path here that goes this one here. I don't know, maybe it goes like this. And if the pieces are V1 up to Vn, then we can also write out what their signatures look like. So the signature of this piecewise linear path with pieces V1 up to Vn is given by this tensor product of x per V1 tensor tensor x per Vn. Or if we wanted to write this out as a power series, we'd get this expression here. Okay, and this is nice because we have a connection between structure at the level of tensors and structure at the level of paths, that taking the tensor product of two signatures gives the signature of the concatenation of the paths. So we can see this here for this linear or piecewise linear setting, but it also holds more generally as well, that concatenating paths corresponds to taking the tensor product of their signatures. So it's this nice algebra compatible way to encode paths where concatenation corresponds to taking tensor products. Okay, so then we can consider tensor decomposition of signatures, or the type of tensor decomposition that these signature tensors really want us to work with. So I said before, if we have a piecewise linear path with pieces V1 up to Vn, then its signature is given by this tensor product of exponentials. So this is a sort of exp rank 1 decomposition, which fits our piecewise linear path to signature. Okay, so then in principle, if we wanted to recover a path from its signature, which is something that we often want to be able to do, then working within this piecewise linear setting, we can aim to find vectors V1 up to Vn, such that our input signature is approximately equal to this tensor product of exponentials. And this is an infinite system of equations, or almost equations, because I'm working in this infinite tensor algebra. But in practice, you can truncate to a particular level of interest and look at the recovery problem there. And this has been studied in some different cases. So in work of Lyons and Chu on inverting the signature of a path, where they look at recovery from possibly infinite signature, or looking at finite truncation in this paper of Amendela, Fritz, and Schoenfels, where they also discuss nice connections between the signature of a path and the moments of a probability distribution. And we focus on recovering the signature, a path from its third order signature, in this paper here, which is joint work with Max Pfeffer and Bernd Schoenfels. Down here. Okay, all right. So what other nice properties does the signature have? Or in fact, what are the properties that enable us to be able to find these types of decompositions? Well, if we take a path and we apply a linear transformation to it, so let's say we have this nice path here, and we apply some group element, and we get this piecewise linear path here, then natural question to ask is, what does this linear transformation do to the signatures? So how does the signature of this path relate to the signature of this path? Well, the transformation transforms the signature under congruence. So this means, okay, V is supposed to be the vector at level 1. So at level 1, we just send our V to G times V. At level 2, the congruence action looks like this. Our level 2 signature maps to G M G transpose. At level 3, it looks like this. So T maps to this represents the new tensor you get by multiplying T by G on all 3 sides. So that's this this product here written out in coordinates, and so on. So at level 4, you multiply by G on all 4 sides, and so on. So this says that if we want to relate the signature of 2 different paths, let's say we have this path here and we know its signature, and maybe at level 3 its signature is given like this, and then we have some other signature and we want to find the group element that transforms our path to this unknown path, or equivalently we want to actually just know what this path is. What this setup is telling us is this is the tensor decomposition that's relevant in this setting. We have some unknown group element, we have 2 known tensors, and we want to find the group element that sends one tensor to another tensor. So here's our known tensor T, and we have this known tensor S. We think that they relate to each other by multiplying by some unknown group element G under congruence, and we want to recover this group element. So that's our decomposition of this tensor. So it's a bit like a Tucker decomposition in that we have some core tensor, which often we want to be smaller, and then we're multiplying it on all sides by some change of basis. But it's also different from a Tucker decomposition in that the core tensor is fixed, and also all 3 matrices that we're multiplying by have to be the same, right? Because they've all come from this original group element here. So yeah, this is an example of a kind of tensor decomposition that arises naturally in the setting of signatures. Okay, so signatures are widely studied and are known to represent paths faithfully in some sense. So the signature is invariant under reparameterization of the path. So if you have two paths that are the same, but one is a reparameterization of the other, it won't notice that difference. And also, if one path differs from the other by a tree-like piece, so this picture describes what a tree-like piece is, then again, the signature won't notice that difference. And in fact, this is known to be if and only if in original work by Chen and later by Hambly and Lyons, where you can characterize exactly when two paths will have the same signature. And here's, this is a picture of two tree-like equivalent paths. So we have our original path, which is this blue one here. Then we have this extra piece sticking out where we go out and then we exactly backtrack and we go out again and backtrack and so on. So the signature won't be able to detect this piece here. So the signature of just this blue path and this whole path here, where we also follow the red arrows before rejoining the blue path, will not be distinguished by the signature. But if we have two paths that are not equivalent under reparameterization, or this what's known as tree-like equivalence, then their signatures will be different. Okay, and this has been applied, for instance, in machine learning pipelines, as I hinted at before. Maybe this is a nice way to encode data in order to be able to tell differences between types of path that arise in different contexts. And for example, it's been applied to look at time series data that occurs in some biological applications. So for instance, in these two references here, 20 and 21, where it's used in the setting of bipolar disorder and borderline personality disorder, and also in looking at sepsis detection. All right, so I wanted to mention these biological applications because it takes me on to the third setting in which we can find tensors in applications. Well, the third setting that I'll talk about today. So first we have probability tensors, then we have these encodings, so moments or cumulants or the signature. And the third possibility is where we have each entry of our tensor representing some data value. Okay, so we have various indices, and they represent things that we're changing in an experiment, either independent or dependent variables. And they might be ordered, for example, spatial or temporal coordinates, or they could be unordered. Okay, so here's the example that I showed before, which comes from the setting of looking at signaling pathways for different cancer cells. So here's the data. You have some cell lines. You expose them to 14 different ligands at one of two doses. You have these two output measurements, and you record each output measurement across 4 different time points. Okay, so you've got your 5 different indices, and once you've fixed a value for each of your 5 indices, you have a number, which is in this case, the phosphorylation of either ERK or AKT at a particular time point, under a particular dose, for a particular ligand, and a particular cell line. Okay, so in situations like this, the data arrives and, well, other people work very hard to produce the data. It doesn't just arrive. And it looks like a tensor. So it has this natural sort of multi-index structure. And we want to understand questions like, how are each of these 5 different variables all related to one another? And perhaps we hope that keeping the data in this tensor format is the right way to approach this kind of question. And one way to think about this is, well, if we flatten the data to get a matrix, what do we lose? So for this particular example, we could think about flattening to just have the rows of our matrix be the cell lines and everything else is combined together. So this would give us a matrix size 36 by 224 for this particular example. And okay, maybe a downside to this approach is that now we don't have very much data. We only have 36 data points, although we have a lot of different measurements for each of them. Or we could think about some other flattening of the data. So we can think of an experiment as being given by the cell line, so what we're experimenting on, and the ligand, so what we're experimenting with. So that would give us a matrix of size 504 by 16, where we have our experiments and then each of the values for our experiment. And yeah, I find these types of questions very, very interesting. So we have some data in a tensor, and there's the maybe practical or theoretical or even philosophical question of what it means to actually find structure among this data. And in this project here, joined with my collaborators, Mariano, Birgit, Mario, and Heather, we look at a particular way to cluster this tensor data to respect this multi-index structure. So we look at a particular structured clustering of the data. And there's many settings in which tensor tools are being used in the study of biological data. So again, this isn't intended to be comprehensive in any way, but it just to give some examples, because I think this is a nice topic. So let's see. So in this paper here, they're looking at neural dynamics. So this is work of Williams et al. And there, the tensor decomposition that they look at is low rank CP decomposition. In this paper of gene expression data of Hore et al., they're looking at a high rank CP decomposition with some sparsity imposed. So they have some three-dimensional data and they decompose it like this. This is taken from their paper. And there are some other examples too. So in this paper of Omberg, Golub, and Alter, they apply the higher order singular value decomposition. In work of Wag, Fisher, and Song, they apply a semi-non-negative Tucker decomposition. So these three papers are all in the context of gene expression data that looks like this. And in this last reference here in work of Church, Barte et al., they look at a fully non-negative Tucker decomposition. So the message from all of this is that there are various tensor decompositions which are being applied in different biological contexts, but probably also much, much more scope to have some nice tensor decomposition methods that give us structure in these biological settings of interest. All right, so I think I'm out of time and I will wrap up. So what I hope to convey in this tutorial was the connections between tensor structure and these applications. So how properties of tensors translate to give us properties of, could be a probability distribution or a path, or maybe even some property of our biological setting. And okay, these applications suggest new tensor decompositions. So we get new tensor decompositions from applications, and then we also get new applications of tensor decompositions. Thanks a lot. That's it.